Good morning. So, in the last class we have talked about that given the probability density function which has a known parametric form, where it is not necessary that the probability density function has to be Gaussian or normal, but if it is having any other form but which can be parameterized, and that is we have the known parametric form of the probability density functions, then it is possible to estimate the value of the parameters from the training samples. And the kind of estimation that we have talked about is maximum likelihood estimation of the parameter vector, that is the value of the parameters which is best supported by the training samples those are given. Okay. Simultaneously, we can also have non-parametric estimation of the probability density function, because in many cases I don't need to know what is the exact form of the probability density function, but what we have to find out is p of x given omega or p of omega given x. So, given a value of x, I have to estimate what is the probability density function for the corresponding, or what is the value of the probability for the corresponding value of x. Okay. So, I need not have the knowledge of the entire parametric form of the probability density function. Rather, if I know what is the value of x for a value of x, and this value of px has to be estimated from the given set of samples. Okay. That is what is called non-parametric form. I can have both types of estimations, whether it is in the non-parametric form or in the non-parametric form. Now, today I will discuss about a problem which is the dimensionality problem. That is, we said that the feature vectors are of dimension d, where every component of the feature vector represents certain aspect of the pattern, or it gives some description of the pattern, which we discussed in our earlier classes when we talked about the feature extraction processes. Okay. So, when I have d number of components of the feature vector, each of these components give you some characteristics of the pattern, and when all these different characteristics or d number of characteristics are taken together, I can have some sort of discriminating power given by these feature vectors among different patterns. Okay. So, today we will discuss that what is the problem if we have more number of features in the feature vector, or if the dimensionality of the feature vector increases. Okay. So, that is what is the dimensionality problem. Now, let us go to the Bayes decision theory or minimum error rate classification, where we said that if I know the probability density function. So, let me assume that we are having two classes. One is class omega 1 and the other one is class omega 2. So, I consider two classes, omega 1 and omega 2, and I also assume that say p of omega 1, that is a priori probability of class omega 1 and the a priori probability of class omega 2, p omega 2, they are same. Okay. So, by assuming this, if I plot the probability density functions p omega 1 and p omega 2, and let me also assume that the variance of these two classes are also same, that is sigma 1 square is equal to sigma 2 square. So, I also assume that along with this. So, p omega 1 is equal to p omega 2. I also assume that sigma 1 square is equal to sigma 2 square for simplicity. That means both the probability density functions, they have the same size and same shape, but the difference is the means are different, that is mu 1 is not equal to mu 2. Obviously, because if mu 1 and mu 2 are also same, that means I have the same probability density functions, they are not different. So, given this, if I plot p of x given omega 1 and p of x given omega 2, so let me plot in this side p of x given omega, okay, and suppose the probability density functions are something like this. So, this is one, this extends infinitely, okay, and the other one is say something like, they have the same form, okay. So, they have same shape and same size, only thing is one is shifted from the other because the means are different, mu 1 is different from mu 2. So, suppose this is for class omega 1 and this is for class omega 2, okay, where this is mu 1 and this is mu 2. Okay. Then we have said earlier when we talked about the Bayes decision theory that whenever the two probabilities are same, that is my boundary. Okay. So, for all values of x which are greater than this, okay, that is p of x given omega 1 is greater than p of x given omega 2. Obviously, it is nothing but p of x given omega 1 into p omega 1, which is greater than p of x given omega 2 into p omega 2. That was our Bayes decision theory. But because here we are assuming that p of omega 1 is equal to p of omega 2, so effectively it turns out to be p of x given omega 1 greater than p of x given omega 2. Okay. So, for all values of x lying on the right hand side of this point, we will decide that it belongs to class omega 2, and for all values of x lying on the left hand side of this point, we will decide that it belongs to class omega 1. Okay. Then we have also said when we talked about the Bayes or minimum error rate classification that the error in taking this decision, because whenever I decide in favor of class omega 2, there is a finite probability that it may belong to class omega 1 as well. Okay. So, the error involved in taking this decision that we said earlier is nothing but the area under this curve. Okay. And it extends indefinitely. So, this is what is the error in taking decision whether I decide in favor of omega 1 or I decide in favor of omega 2. So, this area under this probability curve, that gives me the total amount of error. Okay. Now, find that if I shift this mu 2, that is instead of mu 2 being here, if mu 2 is, so if this for class omega 2, the probability density function is something like this. Okay. So, suppose this becomes my mu 2. Okay. If this is the mu 2, then this is my decision boundary. Okay. And if this is the decision boundary, then the error will be reduced to this. Okay. So, you find that earlier my error was bounded under this curve, now the error is bounded under these curves. So, definitely the total error in the earlier case is higher than the total error that I get in this case when the separation between mu 1 and mu 2 becomes large. Okay. So, when the separation between the two means mu 1 and mu 2 is low, then the total error increases. If the separation between the two means mu 1 and mu 2 is large, then the total error decreases. Okay. So, that clearly indicates that what are the features which are best suitable for classification purpose. Okay. It is the features whose means for different classes are widely apart. Those are the features best suited for classification. Okay. If the means are quite near, very near, then those features does not give you much of discriminating power. Though, even if the means differ by some amount, however small it is, they still have some discriminative power, but the discriminating power of those features where the means are closer, means for different classes are closer, is much less than the discriminating power of those features whose means are widely apart. Okay. So, usual practice in pattern recognition problem is that you start with some features, find out what is the performance of classification. If the performance of classification, that means if the misclassification rate is not satisfactory, that is the performance is poor, you try to incorporate more and more features. Because as I said, if the features, means of the features are different, they are not same, they have some discriminating power. Okay, but the extent of the discriminating power depends upon what is the distance between the means. As the distance increases, the discriminating power increases. As the distance decreases, the discriminating power also decreases. Okay, so if I find that with certain number of features, the performance of classification is not very good, you try to incorporate more and more features. Okay, so if I try to incorporate more and more features, then effectively what I am doing is the dimensionality of the feature vectors I am going to increase. Okay, so the value of D will increase as we incorporate more and more number of features in the feature vector. Okay, but that leads to another problem. Should we go on increasing the dimensionality of the feature vector without any control? Okay, so that is what is the dimensionality problem. So let us see that what kind of problem that we will face if we go on increasing the dimensionality of the feature vector. Okay, so you find that earlier we said that the function gx or discriminating function for different classes is given by minus half x minus mu transpose sigma inverse into x minus mu, okay, minus d by 2 log of 2 pi minus half log of determinant of the covariance matrix, okay, plus log of p omega I. So all these have to be I, x minus mu I sigma I inverse into x minus mu I, and this is sigma I. Okay, so this was the discriminating function for the ith class, right? Now see that what is the amount of computation involved in this particular case. Out of this we said that this term minus d by 2 log of 2 pi, this is class independent, this does not depend upon the class. Okay, so we can as well remove it from the definition of discriminating function, because for all the classes this value will remain, so it does not give you any discriminating power. But the other terms, they really discriminate among different classes. Okay, now from here when I try to compute the value of mu I, okay, you assume that I have n number of samples, training samples belonging to class omega I. Okay, so when I compute the value of mu I is nothing but 1 upon n summation of xk, where k varies from 1 to n, right. So I have to incorporate n number of summations followed by 1 division, and this xk, that is a feature vector of dimension d. Okay, for every component I have to compute n number of summations. That means the total number of summation that I have to perform is n into d, right, and I can assume that for this division it takes constant time. So the computational complexity to find out the mean vector is n into d, which is dimension dependent. It depends upon the number of vectors, at the same time it depends upon d, which is the dimensionality of the vector, right. Now coming to the other term, computation of this sigma I or sigma I inverse. Okay, you find that this sigma I, the definition of sigma I was 1 over n into summation x k minus mu I into xk minus mu I transpose, okay, where k varies from 1 to n, right. So, this is a vector of dimension d by 1, this is a vector of dimension 1 by d, right. So, this is a vector of dimension d by 1, this is a vector of dimension 1 by d. When I compute, I get a matrix of dimension d by d, that is d square. And following similar manner, if I try to find out what is the amount of computation that will be involved in this case for computation of this sigma I, you will find that this takes a computation of the order of n into d square. Okay. So, to find the mean vector, I need a computation of dimension n into d. To find out the covariance matrix, I need a computation of the order n into d square. Similarly, over here, this also takes a computation of order n into d square. Of course, this one is constant, not constant, it depends upon the value of n, because when I want to compute omega I have to take n number of samples in picture. So, this is of dimension n, complexity n. Okay. So, overall, you find that the computational complexity of this discriminant function, because this is the highest one. So, I can take that the overall complexity is of order n into d square. Not only that, I have C number of classes, right. For every class, I have to compute this discriminating function, and then I have to find out which one is maximum. Okay. So, before I get the maximum, I have to compute the discriminating function for each and every class, and have C number of classes. For every class, I have a computational complexity of n into d square. So, for C number of classes, the total computational complexity will be of order C into n into d square. Okay. So, here you find that the computational complexity is linear in terms of C, that is the number of classes, linear in terms of n, that is the number of samples in the class, but it is quadratic or square in terms of the dimensionality, right. So, if the dimensionality is increased by a factor of 2, the computational complexity is increased by a factor of 4. If it is increased by a factor of 3, computational complexity becomes 9 times, right. So, this dimensionality of the feature vector is very, very crucial to determine how efficient your classifier will be. So, it is not always good that you go on increasing the dimensionality of the feature vector by incorporating more and more features. Okay. It is true that if I incorporate more and more features, the classification performance might be better, but at the same time the classifier becomes inefficient. Okay. So, we have to think of the ways in which the dimensionality of the feature vectors can be reduced. That means, whether it is possible that okay, initially I start with feature vectors of higher dimension, but whether it is possible to reduce the dimensionality, but still maintaining the separability power of the selected features. Okay. So, that means what we have to do is, given a feature vector of higher dimension, I have to take the projection of those higher dimensional feature vectors onto a lower dimension, but this projection has to be in such a way that the space of lower dimension on which I am projecting these feature vectors, that space should be as orthogonal as possible. That means, the different features, they should not be correlated. Okay. Because one of the fact is, when I incorporate more and more features arbitrarily, I do not guarantee that all those features will be orthogonal. That means, one feature may have some correlation with another feature, but when I try to project onto a lower dimensional space, I should make sure that this lower dimensional space is orthogonal. That means, whatever feature I try to capture one feature should not depend upon the other feature. So, these features should be independent. Okay. So, coming to this concept of projection, with the aim to reduce the dimensionality of the feature vectors, I can have two types of projections or two types of concepts. So, what we are discussing now is the reduction of dimensionality. That means, initially I have a feature vector of dimension d. I want to reduce these two feature vectors of dimension d prime, where d prime is less than or equal to d. Obviously, I do not want d prime to be larger than d. At most, it can be equal to d, but I target for d prime less than d, so that the dimension is reduced. Now, when I try to do that, there are two approaches. One is PCA, or principal component analysis. The principal component analysis or PCA approach is that you try to project your higher dimensional feature vectors onto a space of lower dimension in such a way that in the lower dimension, whatever feature vector I get or projected feature vector that I get, that best represents the initial feature vector that I have projected, the original feature vector that I have projected. Okay. So, when I say best represents, it is the best representation in terms of least square error sets. That is the least square error between your initial feature vectors or original feature vectors and the reduced feature vectors, that should be minimum. Okay. And the other approach is called MDA, that is multiple discriminant analysis. Okay. So, the aim of multiple discriminant analysis is, after all, why we are doing or trying to manipulate all these feature vectors, because we want to separate among the feature vectors which belong to different classes. So, the multiple discriminant analysis, what it tries to do is, when you take a projection onto a different space, onto a different feature space, it tries to separate the mean vectors of different classes, and at the same time tries to make the samples belonging to the same class more compact. That means, within class scatter is reduced, whereas between class scatter is increased. Okay. That is quite natural, because here what we said is, coming to this diagram, okay, or let me redraw this diagram. This is x, this is Px given omega. Okay. So, suppose the distribution is something like this. So, this is mu1 and this is mu2. We said that if we increase the distance between mu1 and mu2, my classification error will be less. Okay, that is one. At the same time, if I try to reduce the variance of the samples within a class, that means keeping mu1 and mu2 same in the same location. So, this remains mu1, this remains mu2, but now I want to have a distribution something like this. Okay. So, you find that the distance between the means mu1 and mu2 remains the same, but within class scatter or the variance of the samples belonging to the same class, they are reduced. Then also my classification will be better, that is error rate will be less. Okay. So, this MDA approach or multiple discriminant analysis, what it does is it tries to increase the distance between the means, that is the interclass scatter that it tries to increase, and at the same time it tries to reduce the within class scatter or tries to reduce the variance of the feature vectors onto the projected space. So, you benefit in both ways. One is increase the distance between the means and simultaneously reduce the variance within the class, so that the overall error is minimized. So, these are two different approaches. One is principal component analysis, other one is multiple discriminant analysis. Okay. So, today what we will discuss is the principal component analysis approach. Okay. So, we will talk about the PCA or principal component analysis. Okay. So, our problem is like this, that we have been given n number of feature vectors. Every feature vector is of dimension d. Okay. So, I have n number of feature vectors. The feature vectors are x1, x2, x3 up to xn. Okay. Each of the feature vector is of dimension d, right. Obviously, the mean of this set of feature vectors is given by 1 upon n sigma xk, k varying from 1 to n. That is the mean of the feature vector. Okay. Now, let us try to see that initially I have the dimensionality of the feature vector which is equal to d. Let me take one extreme case, that I want to represent this by a 0-dimensional feature vector, right. So, if I try to represent this by a 0-dimensional feature vector, that means within feature vectors I do not have any variance. So, that is nothing but this mean. So, this entire set of feature vectors is represented by mean vector. But while doing that, what I lose is the variability within the data, which is also not good, right. So, instead of 0-dimensional features, let us assume that I want to represent this d-dimensional feature vectors by 1D feature vectors. Pardon? Mean is a feature, but the n number of features it is represented by only one feature vector. While doing that, I lose the variance because I have a single representation. Okay. So, now what I am saying is I do not want to do that. I will represent these d-dimensional feature vectors by 1-dimensional feature vector. I will still have n number of feature vectors. The number of feature vectors will remain the same. So, there will be variability. But the dimension of every feature vector, instead of d, now it will be 1. So, what I am trying to do is a vector getting mapped to a scalar, okay, because I am reducing the dimensionality to 1. Okay. Let me take this step by step approach, that what should be such best type of projection if I want to project in one dimension, and then whether I can project onto multiple dimensions. If I want to project into multiple dimensions, what should be nature of such space? Okay. So, if I want to project onto a single dimension, so suppose I have the set of points something like this, they are arbitrarily distributed, I have n number of such points, okay, and the mean m is somewhere over here. Okay. So, what I do is, if I want to represent these d-dimensional feature vectors by a 1-dimensional feature vector, that means I have to represent these feature vectors somehow onto a line. Okay. the d-dimensional feature vectors somehow will be mapped to different points on a line, right? So let us take a line passing through the mean of these feature vectors, okay, and let me assume that a unit vector in the direction of this line is given by E, right? So I am in space X. Within this space, I have a line passing through the mean of the given sample feature vectors, and the direction of this line I am saying it is E, right? So when I have done this, you find that the equation of this line will be given by x is equal to m plus a e. Okay, because it passes through m, that is the mean of the given feature vectors. Okay, and equation of this line, if a is equal to 0, then x equal to m. That means I am at this point m, right? For different values of a, I am moving from m in the direction of e. That means I am moving along this line. Okay, so this equation of the state line in the direction of e, where e is an unit vector passing through the mean m, is given by x equal to m plus a e, right? And this a now represents positions of different points on this line. Given this, I can represent a point xk on this line, okay, and that xk, point xk, I can represent by m plus ak times e. We will see what will be the value of this ak, the best possible value of this ak. Okay, so for different points, I will have different values of this ak. So this ak represents that a point xk, where is it mapped onto this line? Okay, now while doing this, definitely I have incorporated some amount of error, because xk is of dimension d. I am representing this xk by a line, by a point on the line. So obviously, while doing so, I have incorporated some amount of error. And what is that error? This is nothing but m plus ak times e minus xk. Xk is the original one, and this is the one that I have represented. Okay. So what I can do is, for taken all these lines together or all these points together, I can define an error function or a criteria function. Okay. So that error function or the criteria function is nothing but, let me represent it as, this is the usual way you represent it by j. Obviously, it will be a function of a1, a2 up to an, and it will be also a function of direction of the line, which is e, right? And this is nothing but m plus a e minus xk take the mod square, take the summation over k varying from 1 to n. Okay. So this is a squared error within summation. This becomes sum of squared error, right? And what we try to do is, we try to minimize this sum of squared error in terms of a, right? So I want to find out that what are these a's, or what are the positions on the state line by which my d-dimensional vector should be represented, assuming e to be fixed. I don't touch e for the time being. That is the direction of the line to be fixed. So given a line, how these points are to be mapped onto different points on this line, how the feature vectors are to be mapped onto different points on the state line, so that your sum of squared error is minimized. Okay, so this expression now I can write by slight reorientation. This can be written as ak e minus xk minus m square, take the summation over k varying from 1 to n. This xk is same as the previous one. I just have simply rewritten this. This one. It is then xk I am representing as m plus ak into e. Yeah, see, otherwise how do I get the error? This xk is my original point and this is the projected point. So, the difference between original point and the projected point, that is my error. Okay, I am trying to estimate the error, right? So, this is same as my original xk. So, this one, okay, this, if this square I expand, it simply becomes sum of a square into mod of e square minus 2 summation ak e transpose xk minus m plus sum of xk minus m square. Okay, I am not writing the limits of summation. The limit is n varying from 1 to n. So, this is my sum of squared error. Okay. What I want to do is, I want to minimize this sum of squared error by varying the values of a. Okay. So, what I have to do for that is take the differentiation of this with respect to a, equate that to 0, solve for values of a. Okay. So, effectively what I want to do is, I want to take gradient of j with respect to a and equate that to 0. And by solving this, I get the values of different a. Okay. That comes later. I said I will go stage by stage. Initially, I am saying that assuming the direction of the line to be fixed. Let us not try to handle all together. Dimensionality of E is same as D, because it is an unit vector in the direction of the line in D-dimensional space. Okay, it is a vector in D-dimensional space. So, obviously, the dimensionality of E will also be D. If I want to represent a vector in 3-dimensional space, the dimensionality of the vector is obviously 3. Okay. So, when I take the differentiation of this with respect to A, what I get is, so effectively del j del A is nothing but 2 into summation of ak minus 2 E transpose xk minus m. Okay. So, if I take the differentiation of this with respect to a, okay, then what I get is, if I take the differentiation of this, and what I forgot is the mod of E, that is equal to 1, because it is unit vector in the direction of the line. So, mod of E is equal to 1. So, effectively what I have is summation of ak square. Take the differentiation, that becomes 2 times ak. Okay. Take the differentiation of this, I get, because it is ak into et transpose xk minus m. So, if I take the differentiate with respect to a, I am left with simply et into xk minus m, e transpose xk minus m. This term is independent of a. So, differentiate this with respect to a, it becomes 0, right. So, after differentiating this term, assuming by making use of the fact that modulus of E is equal to 1, I get this output, right, and I have to equate this to 0 for minimization. Okay. So, when I equate this to 0, I get simply ak is equal to E transpose xk minus m, right. Equating this to 0, I get AK is equal to E transpose xk minus m. Now, what is this? E is an unit vector in the direction of the line, right. So, this simply says that AK is nothing but orthogonal projection of xk onto a line in the direction of E passing through the mean m. Okay. It is just orthogonal projection of point xk onto a line in the direction of E passing through the mean point m, right. So, simply what we get is, when I have these sets of points, this AK represents these projected points onto this line. And how do I compute this? This is nothing but projections of different AKs onto XKs onto this line. Okay, and this projection is nothing but an orthogonal projection, and that gives me the position AK. Okay. So, the best kind of representation in one dimension is to project the d-dimensional feature vectors, take the orthogonal projection of the d-dimensional feature vectors onto a line passing through the centroid. Okay. So, now you see that our assumption was we started with a given line whose direction was known as E, and for the given line the best type of representation is taking orthogonal projections onto that line. Okay. So, given a line, the best representation is orthogonal projection onto the line. Now, which given line is best? That is the question that he has raised. So far, we have considered that our line is given. Now, which particular direction of the line is best? That is, what direction is best? Let us try to answer that. Okay. So, for doing this, I start with the same one, that now I have to find out the direction of the line, that is E. Now, A, I have determined that to find out A's, it has to be orthogonal projection. Now, I have to determine that which direction of the line or which line will be best. That means, what should be best E. Okay. So, I write this J, the criteria function, as a function of E. You remember, this E is not error. I am not saying this as error. Okay. This is the unit vector in the direction of the. Okay. So, J E is equal to AK square, okay, minus, what did I have? What is that expression? Yeah, minus, yeah, A is a vector having different AKs as components. When I say differentiation, it is gradient, because in the vector space I cannot take differentiation. In the vector space I have to take gradient, which are nothing but components of that gradient comes as partial differentiation with respect to individual components. Okay. So, I had this J E is equal to AK square minus AK E transpose, okay, xk minus m, right, plus sum of xk minus m square. I am not writing the limit of summation. Okay. Now, this AK we have found that it is same as E transpose xk minus m. Okay. So, this I can simply write as this one. So, this will be AK square, this will also be AK square, this is minus 2 AK square, minus 2 summation of AK square, this is plus summation of AK square. So, effectively I get minus summation of AK square, and AK is nothing but E transpose xk minus m. Okay. So, I can rewrite this expression as minus summation of E transpose xk minus m into xk minus m transpose into E. See, here what I have is, this is ak square, this is minus, there should be a 2 over here, yeah, minus 2ak square, because E transpose xk minus m is nothing but ak. Okay, so effectively I have minus ak square plus ak square minus 2ak square. So I have minus ak square, and ak is nothing but E transpose xk minus m. So it is minus summation of E transpose xk minus m square. If I break that, I can write this as E transpose xk minus m into xk minus m transpose E. It is in the matrix expression, it is same. Okay, so this plus sum of the other term remains as it is, xk minus m square. Okay, now this E is independent of k. So these E terms I can take out of summation expression. Okay, so this I can write as minus E transpose summation xk minus m into xk minus m transpose E, because E is independent of k. So I can take this E out of the summation expression, because this summation is over k varying from 1 to n, right, plus summation of xk minus m square. So it remains the same, right. Now you find that what is this term, sum of xk minus m into xk minus m transpose. If you remember from our earlier expressions, what is our covariance matrix sigma? 1 upon n summation xk minus m into xk minus m transpose, take the summation k is equal to 1 to n. Okay, and here you find that this term is nothing but a scaled version of this term. So if I multiply this covariance matrix, this is 1 upon n, sorry. If I multiply the covariance matrix by n, which is the number of samples over which I am trying to compute the covariance matrix, I get this term. Okay, and this is what is called scatter matrix. Okay, so it simply represents that how the data is spread in the space. Okay, because you remember that from your one dimensional Gaussian function, if variance is more, the curve becomes flat. If the variance is less, the curve becomes sharp. That means the point is distributed over a smaller space. If the variance is small, the points are distributed over a larger space if the variance is large. Same is for covariance matrix. The covariance matrix tells you shape as well as size. That means to what extent the data is distributed and whether the data distribution is oriented in some particular directions or not. That is what is captured by covariance matrix. Okay, so same is the case of scatter matrix. Scatter matrix gives you the same information, but with a scale factor of n. So if I multiply covariance matrix by the number of samples n, I get the scatter matrix, right. So this expression now becomes this JE. So if I simply rewrite this, it becomes JE is equal to minus E transpose S, that is the scatter matrix, E plus summation of xk minus m square. Okay. Now what is our m? I want to minimize this JE by varying E. This should be within bracket as a function of E. JE by varying G, by varying E. And you find that this term is independent of E. So if I want to minimize JE, what I have to do is I have to maximize this. It is effectively same. Minimization of JE effectively means maximization of minus E transpose S, sorry, maximization of E transpose SE. So, if I maximize this E transpose SE, effectively I am minimizing this criteria function JE. Okay. So, what I have to look for is the maximization of this E transpose SE. And for this maximization, if I make use of Lagrangian, okay, so I can have an expression of the form U is equal to E transpose SE minus lambda E transpose E minus 1. So, I have to maximize this using Lagrangian subject to the constraint that mod of E is equal to 1. Okay. So, to maximize this, what I have to do is I have to take the differentiation of this with respect to E. So, what I have to compute is del U del E, and if I compute del U del E, then over here I simply get expression 2 S E minus 2 lambda E. Differentiate this with respect to E, I get 2 S E minus 2 lambda E. I have to equate this to 0, right. So, if I equate this to 0, I get simple expression S E is equal to lambda E. Okay. What is this expression? This is an eigenvalue expression. So, this is simply an eigenvalue expression. Okay. Where the vector E is an eigenvector of S. Okay. And what is lambda? It is the corresponding eigenvalue. Okay. And now you remember that I have to maximize, or aim is to maximize E transpose SE, right, where SE is equal to lambda E. That means I have to maximize E transpose lambda E. Our constant is modulus of E is equal to 1. So, if I want to maximize E transpose lambda E, that means I have to take the maximum value of lambda. Okay. So, that effectively says that when I am considering the direction of the line in the direction of vector E, from here I find that this E is nothing but the eigenvector, and which eigenvector I have to consider? The eigenvector corresponding to the maximum eigenvalue. Okay. And by using this, whatever value of A I get, because my ultimate aim is I have to find out, get the value of A k, that is what represents the point. Okay. So, that value of A k is called the principal component. That is why it is principal component analysis. Okay. People also call it KL transformation. Now, you remember how this KL transformation came into picture? You had the covariance matrix, take the eigenvalues of the covariance, eigenvectors of the covariance matrix corresponding to the largest eigenvalues. Okay. From that you form a transformation matrix, and the transformation that you get is KL transformation. That is nothing but this. And there we said that whenever we talk about the KL transformation, we talk about principal component analysis. And why it is principal component? This is the reason it is principal component. Okay. So, here you find that if I take only one eigenvector corresponding to the largest eigenvalue, then the corresponding principal component is a scalar one, and effectively my d-dimensional feature vector I am converting to one-dimensional feature vector. Okay. Now, instead of considering only single eigenvector, if I consider multiple numbers of eigenvectors corresponding to the largest eigenvalues. So, instead of considering only one eigenvector, if I consider d prime number of eigenvectors, where d prime is less than or equal to d, corresponding to d prime number of largest eigenvalues. Okay. Then take the orthogonal projection of your feature vector, d-dimensional feature vector, onto those eigenvectors. The corresponding principal components of the projection values, projections that you get, that gives you d prime dimensional feature vector. Okay. And because my scatter matrix is real and symmetric, the eigenvectors are orthogonal. That means the principal components that I get, they are also orthogonal. And because they are also orthogonal, one is uncorrelated from the other. Okay. So, if I go for this principal component analysis, I can reduce the dimensionality. Simultaneously, I also ensure that my d prime dimensional feature vector that I will generate, those feature vectors will be where the components will be uncorrelated. That means every component of the feature vector gives you independent information, which no other component will give. Okay. So, let us stop here today. We will continue with MDA approach in the next class.